At the end of each of the PowerPoint files about the curved mirrors and lenses, there's a couple of interesting slides about spherical and chromatic aberration. So what are these things? Well, they have to do with the position of the focal point. When we talked about mirrors, we tried to find the focal point. We said that incoming light rays that were parallel ended up at a single focal point. Now, the proof of this has an interesting side effect. So, light coming in here reflects off the mirror. Now, the angle of incidence must equal the angle of reflection. That's the law of reflection. But if you look carefully, you can see a Z here. So this angle and this angle are alternate angles. So this must also be equal to the angle of incidence. Now look at this triangle here. I've got two angles the same, which means it's isosceles. So this length is the same as that length. Now, provided I don't go too far away from the centre, and that's the key, provided I don't go too far from the principal axis, this length here is pretty much the same as that length there. Now, the further you go away from that central principal axis, the further out you go, the less close these two lengths are. But when you're close to the principal axis, that means that this length is the same as this length, and the focal point is halfway to the centre of curvature. The thing is, the further you get from the principal axis, the worse it gets, which means that curved mirrors cut on a circular basis, cut as a spherical mirror, actually don't have a single focal point. It's blurred out because light rays that come in further out from the centre end up bending more because of that approximation. This is called spherical aberration. A mirror cut in a circle cannot solve this problem. But there is a solution, and the solution is a parabolic mirror. A parabolic mirror, or rather a parabola, is defined by a single focal point. If you've done the loci of points in Maths C, you will know this. The directrix and a focal point defines the parabola, so that these light rays coming in on a parabolic mirror will all reflect to the single focal point, no matter how far they are from the principal axis. Now, lenses also suffer from spherical aberration, and they have the same solution. Use a parabolic lens instead. But lenses have another problem. It's called chromatic aberration. The thing is, and it's about the way refraction happens, blue light is refracted more than red light. So blue light coming in here is bent more by the lens and ends up at a focal point closer to the lens than the red light, which means that the focal point is different for different colours of light. Now, spherical or parabolic, you can't solve it like that. You cannot avoid this problem. Blue light bends bigger. It's just the way refraction happens. But there is a way to try to work around it. This isn't perfect, but it's not too bad. What you do is you come up with an achromatic doublet or an achromatic lens. You have two different kinds of glass. One bends the light one way and the other bends the light a little bit the other way. So what ends up happening is you cancel the difference between blue and red by using the two different kinds of glass. You end up with a combined focus. It's not perfect, but it's a lot closer.